All right, so I'm going to go over a general overview of chapter two in terms of limits, of functions, eventually what they mean and how to graph them, looking at their limits and their evaluations. And like I said, I'll get to all this stuff little by little. So first, let's start out with a function, talk about a limit, and we're going to kind of do it like rudimentary, which is just taking values that are extremely close to a particular number. So first, a limit. So if I say the limit, the limit as x approaches a of f of x is equal to L, what this means is as the x value gets really close to a, so as x approaches a, then that means that the y value f of x is going to approach this L. So if I have a picture of a graph right here, some green graph, and here's my function f of x, so this is f of x, and I have a value that's a right here, if I pick an x value that's kind of close to a, like this x value right here. Now it's not exactly close to a. Well, I guess it's close in the real terms of infinity, but it could be closer. If I put it right here, you'd be a little bit closer. I put it right here, it'd be a little bit closer. But these are the x values of this particular curve. So this x value has has that y value, right? And then this x value, if I pick it, it's going to have that y value, and this x value, if you pick it, these points right here, it's going to have this y value. The question is, as x gets really close to a, as x is approaching a, this f of x or this y, so let's really call it what it is. Instead of y, let's call it f of x, because it's x, f evaluated to x is your y value. That means this f of x is going to approach, well, you can see if I dotted this up to the curve, set back here, you're going to get L. So you get the value, you get the value L. So as x approaches, the a value, a is on the x-axis, your f of x is going to approach your L value, which is going to be your y value. Now it doesn't matter what direction, if I started x over here and I slid it, the y value is eventually going to slide down to L as well. Now this is really useful. Well, it's really useful to be able to find limits if the function is defined at a. I could literally just plug in f of x is f of a and find its limit. But the problem is there are some curves that have a hole at that particular value. So another curve might look just like this, except it has a hole at this a value. So let's make it look exactly the same. So there, except at this a value, it's got a tiny little hole in it. And the question is, as you get really, really close to that a value, this is my a value. As I start picking values that are really close to a value, you can see that these y values are going to look really close to, that value right there, which is going to be L. But I can't just simply plug in a. If I plug in a, you get undefined. So, in this particular function, since this point lives on the map, f of a is just equal to L. So the limit of as x approaches f of x ends up just being f of a. So just stuff in a, you can find the value of L. But when I have this, if I say what is f of a, well, if it's got a hole here, it's undefined. Undefined, if I can spell it. Not even close. Let's try that again. Undefined. Beautiful. Okay, so even though the function is undefined at a, it means it still has a limit. Because the limit's not actually asking what is the value at the point. The limit's actually asking what is the value you get when you get really, really close to that point. So, as x values get really close to a, these points are still approaching that open circle. So that means these y values are still approaching, this value right here, which still happens to be L. So the question, what one of these functions have a limit? Well, they both have a limit. This one just happens to be defined at f of a, so you can find its limit by just plugging in f of a. This happens to not be defined at f of a, so you have to find values that are really close to it, and then see what their y value ends up being. So one way to be able to do that is using a table, which I'll get to in a minute here. But the true proof, if you want to actually verify that it's a limit, you have to use algebraic methods. So a table is a good estimation, but it's not a proof. You can't guarantee if you keep picking closer and closer numbers that the function's not going to change dramatically. All right, so let's just start with the picture. Let's find some limits right here. So I got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. Let's even go down one. 1, 3, -1. Okay. So I'm gonna just draw a function in here. I'm gonna ask some questions here. So this right here, it's gonna be defined here. And here, open here. Let's do this one. Here, open. Here, closed. Let's go down here. Open, and then this. Perfect. That's enough examples. So this, this green value is my y is equal to f of x. It's my function f of x. So whatever it might look like, I can create a function and make it look like that, but it's piecewise and it's a little messy. But if I have a graph, we'll do with expressions soon enough. But let's talk about graphs first. So I want to know what is the limit as x approaches 0 of my f of x, of this function right here of f of x. Well, as I approach x is equal to 0, which is that value right here, what you're asking about is as x gets really, really close to 0, what does y get really, really close to? So you kind of think of being on train tracks. As these x values get close to 0, you actually live on the curve. So as they get close to 0, we can see that the y values are getting close to, they get close to 1. And even if you come from the other direction, because it has to work both ways for the limit to exist. So if you come from this direction as well, you can see that I'm still approaching that number right here. So the limit is equal to, it's equal to 1. It's that value right there. It's that 1. It's approaching 1. B. What is the limit as x approaches 1 of f of x? Well, as I approach this number 1 here, again, I'm going to get values that are close to 1, so you're living on the train tracks. As you get close to 1, the points actually live up here. So as I get close to 1, you can see that as I get close to 1, this is going to go close to 3. As I get close to 1 this direction, close to 1 this direction, you live on the curve. This is also getting close to 3. The difference between this one and this one is this function is not defined at 1, but I'm not asking what is f of 1. I'm asking for what's the limit as x approaches 1 of f of x. I'm actually asking, when I get close to 1, what does the function get close to? Well, as I get close to 1, both directions, they get really close to 3. So this is equal to 3. Hey, Max, you don't have to join. I'm just recording a lecture for you guys. So you're welcome to just watch it later, or you're welcome to stick around and ask questions. So if you're free and you want to, it's up to you. If you want to go, you're not required. All right. So as I get close to 1, you can see that f of x. As I get close to 1, f of x is getting close to this 3 value. So that's why the limit as approaches 1, it goes to 3 from both directions. Now, C, if I ask you what's the limit as x approaches, let's say 2, as x approaches 2 of f of x. Well, if I come from the left of 2, so here 1, I'm getting closer to, so I'm actually living up here, so points are doing that, right? Hey, Jake, you don't have to stick around if you want to. I'm just doing a lecture. So I'm recording it right now. So if you want to pick it back up off of Canvas, or if you're welcome to stay. I'm not kicking you out. So if you have questions, you're welcome to stick around too. But you're not required to go.
I just joined to kind of see what this was. I'm actually watching 2.6 right now, Infinite Limits on Canvas right now. Okay, I was just making sure.
Yeah, I'm going to basically do 2.1 through 2.6. It's just going to be like a lecture-based explanation.
Oh, okay. All right. Thank you.
Yeah. So as I get approached, if I go from 2 from the left, I can see I'm getting really close to this 2. So if I'm coming to this 2 from the left, the y value is getting really close to this 2. And then if I come from the right, well, the y value is it's 0 every single time. So as I get closer to 2, the y value is still going to be 0 every single time. But the problem here is it approaches 2 from the left, but 0 from the right. So what we'd say is the limit does not exist. For the limit to exist, it has to go to the same direction from both sides. Regardless if there's a hole or not, regardless if it's even defined there. And what's interesting also is if I put a value for f of x, if I say, I can even drop a value right here. Say, well, f of 1 is equal to 1, but its limit is different. So if I ask you, for instance, D, what is just f of 1 equal to? Well, that's different than asking what's the limit as x approaches 1. What I'm actually asking here is what is f exactly at 1? You know, if I plug in x is equal to 1, I'm going to get y is equal to 1 as well. So if I plug in 1, this is the point 1 comma 1. So plug in 1, you get 1. So plug in 1, I'm going to get this, that 1 back, that blue one back, the y value of 1. And notice that their limits and their evaluations are different. And that as I get close to 1 from both directions, as I get close to 1, the y value is getting close to 3. But exactly at 1, I'm equal to 1. So that's why the evaluation is different than the limit. At this particular value here, if I asked you what is f of 0, if I asked you, say, e, what is f of 0? Well, if I plug in 0, I get 1 back, so this is equal to 1. So again, exactly at 0 is equal to 1. Notice that since this point is filled in, the limit and the evaluation are identical, but since this point has got a hole here, the limit and its evaluation are different. So that's the difference between the function being possibly undefined or removable discontinuity. What I did is I removed this point. If you picked it up, I removed it, put it here. So both are values of removable discontinuities, but this one I just plopped a point here saying, well, at f of 1 it's equal to 1. Okay, so let's find a limit of a function, and then I'll graph it and explain how we're going to get this. So we're going to do limits two different ways. I'm going to use a rational expression because it's really nice to graph. I'm going to find its limit using a table, and then next I'm going to find its limit using algebraic means, and then I will draw a picture and show you what's actually happening here. So, example, given f of x is equal to, let's say, x squared minus 25. No, let's make it smaller. X squared minus 9 all over x minus 3. Classic. Okay, so what I want to do is I want to find using table to evaluate, the limit as x approaches 3 of x squared minus 9 all over x minus 3. What's the limit of this f of x? And then B, I want to use algebraic methods. Mary, you don't have to stick around if you want to. This is not required. You're welcome to watch the recording. I'm going to post later. But I'm not kicking you out. If you want to stick around, you're welcome to. So B, what I want to do is I want to use algebraic methods to evaluate. All right, so the same thing. So the limit as x approaches 3 of x squared minus 9 all over x minus 3. So we're going to do the exact same function. And I'm going to draw a picture and show you what it looks like. Okay, so using a table, what we're going to do is we're going to have x values, and then we're going to have f of x values. Remember that this thing right here is f of x. It's f of x. So it's your y values. And what I'm going to do is I'm going to pick numbers that are kind of close to 3. I'm going to start at maybe let's start below it. So if I go like 2.9, that's pretty close to 3. Or I can get even closer, 2.99. Or I can get even closer, 2.999. Like I can see that I'm approaching 3 relatively quickly. So if I have an x-axis, there's my 3. 2.9 might be here. 2.99 might be there. 2.999 might be there. You can see that I'm getting closer and closer to 3. Now I know I can't plug in 3. If I try to plug in 3 into this expression, well, 3 minus 3, I'm going to have, 3 minus 3, I'd have something, over 0, wouldn't I? Which is undefined. So I can't just evaluate this function at 3. It's undefined at 3. So I can't plug in 3. That's not going to work. All right, so then I approached it from below. I also have to approach it from above. I have to make sure it works from both directions. So I'm going to do, I'm making it look kind of nice. I'm going to go like 3.1, 3.01, 3.001. You can see that I'm approaching 3 from this side. I'm also approaching 3 from this side. I'm approaching 3 from below, and I'm also approaching from above. So I'm going to pinch at 3. All right, so I'm gonna use my calculator because I'm lazy. So clear. So what I'm going to do is graph y equals And when you plug this into your calculator, you're going to really want to make sure that it knows what's the top and the bottom. It doesn't understand that bar. So don't forget to put parentheses around these if you're going to try to plug those expressions in. It'll be much different. What you'll actually be plugging is, if you don't put parentheses, that's what the calculator thinks what you're plugging in. So, which is not what we're looking for. Okay, so parentheses x squared minus 9, close parentheses, divided by parentheses x minus 3. You can see it's just enter. Now, this, I'm not looking for a graph, I'm looking for a table. So, on my, where it says window, which is the second button here, if I hit second window, I just want to make sure that independent variable is on ask. And then I'll be able to plug in the numbers that I want. So then instead of hitting graph, I'm going to hit second graph, and it's going to give me my table, and I'm going to populate it really quickly. So 2.9, enter, 2.99, enter. This is the same thing as if I'm plugging 2.9 into this function and just doing them all by myself. So I just don't want to do it 6 times. Well, just make your calculator do it for you. So 2.999, boom, okay. And I can come from the other way, so 3.001, 3.001. Okay, so when I evaluate those, that's if I plug in 2.9, I get 5.9. Then the next one I get 5. If I plug this number into here, I get 5.999. If I plug this number into here, I'm going to get 5.999. If I plug 3.1 into here, I actually get 6.1. If I plug 3.01, I get 6.01. If I plug in 3.00, I get 6.001. So the question is, what am I getting close to? What are these y values getting close to? So, as x, gets close to 3, what's f of x, getting close to? That's really what a limit means, right? What's this thing right here getting close to? So I can see it's getting close to 6. So the answer to this is, is equal to 6. All right, algebraic methods. This provides proof. This is verification. So what we're going to do is I'm going to look at this expression, and I'm going to algebraically manipulate it. And most of that comes down to like factoring or using, multiplying top and bottom by the conjugate. Multiplying top and bottom by 1 essentially is what we do a lot. So I can see that x squared minus 9 factors. So when it's irrational and it factors, clearly that's the method. So x plus 3 times x minus 3, that's the numerator, difference of squares, all over x minus 3. And we can see that that this x minus 3 cancels. So this is equal to the limit as x approaches 3 of just x plus 3. Now, what I'm really looking for a limit is I was really hoping I can just plug this number in. That's the first thing we're going to try. Sometimes, sometimes the graph meets, sometimes it doesn't. And when it doesn't, you'll get 0 over 0 or something over 0. You'll know. The denominator will be 0, so it'll look like this or it'll look like this, kind of. But it doesn't meet. So I can't plug in 3 here, but notice this new expression here, this new expression, I can actually plug in 3 here. So here's a quick question. I'm going to kind of put it up here. So just a really quick question. Does x squared minus 9 all over x minus 3 actually equal x plus 3? Are those things actually equal? This simplified to this, which simplified to this. So are those two things equal? We'll get to it in a minute. Okay, so I noticed that this expression here is defined at 3. So that means I can take that x value of 3 and just plug it right in. So, this 3 value right here is going to go right in that x position. I'm just putting it in the x position. So this is going to be 3 plus 3. That 3 went in there. 3 plus 3 is equal to 6. You can see it's the same value we got here. All right, back to this question. Let's graph them both. So if I graph f of x is equal to x squared minus 9 all over x minus 3, what you'll notice is it gives you a graph that looks very similar to g of x, which is equal to x plus 3. So if I graph both of these, what do they look like? Well, if you already graphed it, if you hit graph, you can see that, there's my line. It actually gives me a line back. It actually gives me this line right back here. So I know it's got a y-intercept of 3 and a slope of 1. So 1, 2, 3, 4, 5, 6, and a slope of 1. So there goes 3. All right, so if I graph this function, it gives me this thing, and if I graph this function, it gives me, well, it's almost the same thing. 1, 2, 3, 1, 2, 3, 4, 5, 6. If you graph this one, it gives you this. And what you'll notice is that the two lines are dang near identical. They're almost the same. They're almost the same. Like when I asked you, are these two things equal? So almost. They're really, really close. Actually, they're equal for every number except what? What x value do they fail at? You know, what x value that do these two functions give you a different answer for? It's kind of the question. Well, the answer is every number but that one, right? Can't plug in 3. You know, if I plug in 3, the bottom is going to be equal to 0. So, but what's neat is if I plug any number besides 3 into this function, and because that's what I did. Remember, I plugged these values into this function here. You know, that's what I put in there. And if you were to plug these values here into this function as well, into that function, you'll get exactly the same value because you can see that for those values are the same. Like, you know, this value, this value, this value, you know, those exact 3 same values are going to give you the exact same y values back. The only place they're going to differ on a y value is when you plug in 3. If I plug 3 into here, you get undefined, but if I plug 3 into here, you get 6. So that's what we do in order to find the actual limit is, I don't really care about what it is at 3. What I do is I care about what it is really close to 3. And what it is really close to 3 on this function and what it is really close to 3 on this function are always going to be the same. So I can use this function to estimate this function for all numbers besides that, you know, that 3. So that's how we get to plug it in. Okay. Next, other limits. So if I ask you to use algebraic methods, you have to use algebraic methods. If I ask you to use the table, then please use the table. So let's just do another one, just finding limits. But we're going to do algebraic. So example, use algebraic. To evaluate. So we have here we go. Okay. So our three main methods well, our main method of limits is using algebraic manipulation. We're just going to factor or use conjugates. We're basically taking advantage of multiplying top and bottom by 1. So I'm going to start out with B first because I think it's the most obvious, and then we're going to get to the other ones. So what I know is that both of these functions share a, I wonder if that's even going to work. Let me make sure. There's no way that's going to work. That's going to work. They say it does. I don't know, let's try that. Let's see. Okay, so what I noticed that that's greatest common factor kind of stuff. So the top, this is going to be the limit as x approaches 0 of, they both share a y squared, actually a 2y squared. 2y squared out here, I'm going to get a 2y plus 1. And on the bottom, these also share a y squared. So I'm going to get a y squared, and this is going to be y squared minus 1. That's why there's no way that's going to work. Some of them must not have a defined limit. Should have practiced, should have grabbed a couple before I started. It doesn't matter. So these are gone. And this is going to be the limits as x approaches. Oh, if that's where it was. That doesn't matter. Let's keep going. Just I'm going to factor and see if I can do it now. My bad. So what I'm really looking at is I want to know when is this function, defined at that particular number. So right now I can't plug in 0 because if you plug in 0 here, 0 here, 0 here, 0 here, I'm going to get a bunch of zeros. 0 plus 0, 0 minus 0. You're going to get 0 over 0. So that 0 over 0 is a it's kind of a red flag marker to say that you're going to be able to probably get a limit here. So that means you're going to be able to cancel off some common factor that's going to make everything 0. And that common factor happened to be y squared. So I factored a y squared out. And when I go back to this function, can I plug in 0 now? Well, I don't care that I'm plugging 0 into the denominator. What I care about is what happens when the entire denominator is 0. But if you do that, this is going to be 2 times 0 minus 1. This is going to be 0 squared minus 1. When you plug in 0, the entire denominator is not 0. The denominator is negative 1. So that would be 0. So 2 times negative 1 is going to be minus 2. All over 0 squared minus 1 is minus 1. This limit's just going to be equal to 2. A similar thing here. This is just manipulating, just factoring. So common denominators and stuff like that. So x to the negative 1 means this is 1 over x. It's x of a power of 1 on the bottom. That's what that negative 1 means. I have an x to the 1 in the denominator. Minus 1 all over x minus 1. So what I have is this really means it's a complex fraction. I have fractions and fractions. I have more than one fraction bar. So what I'm going to do is I'm going to combine this numerator. I'm going to combine this numerator to become a single term, and I'm going to see if I can't cancel with this x minus 1 somehow. So if I can make this a single fraction bar, it's kind of what I'm looking for here. So in order to subtract these two fractions, this 1 over x and this 1, this has to have a common denominator. So I'm going to multiply top and bottom of this 1 by x over x. So you're going to get the limits as x approaches 1 of 1 over x minus, well, 1 times x is x, 1 times all over, well, this is 1 times x. This will also be a 1 times x. So this is going to be x over x, all over x minus 1. Now almost done. So I can combine that numerator because they both have a denominator of x. So limit as x approaches 1 of 1 minus x all over x, common denominator, this minus this. Keep the numerators, keep the denominators and subtract the numerators, all over x minus 1. So now this numerator is one singular fraction as opposed to, two rationals. So I'm going to call the bottom all over 1, and I'm going to take care of this division by multiplying by the reciprocal. So the limit as x approaches 1 of 1 minus x all over x multiplied by the flip at the bottom by the reciprocal at the bottom. Now my claim is that this 1 minus x and this x minus 1 actually share a common factor. And if I cross those out, you actually get -1. And I'll kind of show you why. So limit as x approaches 1. So if I factor in -1 out of this binomial right here, well, this 1 is going to become negative and that x is going to become positive. That x is going to become positive and that 1 is going to become negative. So this expression and that circled expression are equal. Doesn't matter their order, their signs have to stay consistent. So it's still a positive x and a negative 1. So now they cancel, those cancel. So like I said, when you cancel these two things, you get -1. So this is going to be equal to the limit as x approaches 1 of -1 all over x. And this function is now defined at 1. I can plug it in. So -1, plug this 1 into here, this 1 is going to go into the x position, right? So this is going to be -1. And the last method would be conjugate. So when you're looking at conjugates, for instance, if I have a plus b, so this is my binomial, and then the conjugate is going to be equal to a minus b. So whatever your two terms are, they're going to switch the sign between. So if this is going to be minus, then its conjugate is positive. So for all binomials, that's its conjugate, is the opposite in between the two numbers. So what I have is I have a binomial down on the bottom, and I'm going to conjugate it. The radical is really what I'm identifying. So I'm going to multiply top and bottom by the conjugate of this denominator. Now this is two terms. I have one term, it's being grouped by that radical, and another term. So this is a minus b. So that means what's going to happen here is it's going to be a plus b. So it's going to be root x squared plus 5 plus your 3. Same thing on the top. Root x squared plus 5 plus your 3. Remember, it's a binomial. It's two terms. The radical is grouping it. All right, so now we're going to multiply top and bottom together. Only multiply the things that are conjugates. So these numerators are not conjugates. So I'm going to leave them kind of grouped like this, and you'll see why in a minute here. Only multiply the things that are conjugates. Because when you multiply conjugates, beautiful things happen. So I have to FOIL these first. So root x plus 5 times root x plus 5 is going to be root x squared plus 5 squared. It's times itself, so it's squared. And then outside, I'm going to have plus 3 times the square root of x squared plus 5. Inside, I'm going to have minus 3 times the square root of x squared plus 5. And then the last, I'm going to have minus 9. And nice things happen. For instance, these are opposites. 3 of something and -3 of something will add to 0. And this also cancels. This radical cancels with that square. So what we actually get on the bottom is going to be x squared plus 5, and we still have minus 9. So in the denominator, we're actually getting x squared minus 4. All right, we're almost done. X squared minus 4 factors. That x squared minus 4 factors of factors, it's a difference of squares. You're going to get x plus 2 times x minus 2. And we can see that these things cancel, which is the problem with that -2. If I plug -2 into here, I'm going to get 0 over 0. So now I've taken care of that problem factor. I get to plug it in now. So this is going to be 2 plus 5 under the radical, plus 3 all over, plugging in -2 in here, minus 2, minus 2. And minus 2 is going to be minus 4, so the bottom is not 0, so that's good. This is 4 plus 5, which is 9. Square root of 9 is 3, so this is 3 plus 3, which is 6. So again, minus 3/2. All right, one-sided limits. One-sided limits are only done differently if the function is different on two sides of the curve, or two sides of that x value. So, you know, from the left. And then from the right. And it could happen that they don't have the same value. You know, one function might look like this, and another function might look like this. So it's possible at this a that you get two different values. You know, this one might be L and this one might be M. You know, this one might be L. So I'm approaching from the negative side as opposed to approaching from the positive side. So this is A. This is A from the negative side. A from the negative side would be equal to L. Then A from the positive side would be equal to, well, this would be M. M is the negative number, clearly, but it would be M. So what really shows itself with these are piecewise functions. So if I ask us to evaluate the limit, of this, so this way, f of x is equal to, and we can do this as a piecewise, it'd be like 2x plus 1 when x is less than 4, and it could be x squared when x is greater than or equal to 4. So if I ask you A, what is the limit as x approaches 4 from the negative side of this f of x? You know, that function right there. I just don't want to write that function. You could write it as the limit of this thing. It's not wrong. It's just messy. And the other one I want to ask is what if I go from the other direction? What is the limit as x approaches 4 from the positive of the same function of this f of x? Well, I can draw you kind of a picture of what this thing looks like. 1, 2, 3, 4. I know if I'm below 4, it's going to be this line. It's going to have a slope of 2 and a y-intercept of 1. So it's going to have a y-intercept of 1 and a slope of 2. So it's going to look something like this, right? And I can see it's an open at 4, so it's going to be an open circle at 4. Now x squared at 4, you know, x squared looks like a parabola. You know, x squared would look like this, right? But it's only for values above 4. So, you know, x squared probably is going to look like, you know, it's probably going to be something, I don't know if it's below. Let's see. X squared equals 1. Yeah, it's going to be. Now the quadratic, sorry, it's going to be up here. It's going to be the rest of that parabola. No, the rest of that parabola. And that'd be all the values above 4. So 5, 6, 7, and so on. So in this case, I'm asking if I'm below 4. Well, the question is, if I'm below 4, am I going to use this line, the 2x plus 1 line, or am I going to use the x squared line? That's kind of the question. You know, just depending on what side of 4 you're on, right? Well, if I'm less than 4, you know, if x is less than 4, you know, the arrow points that way, I'm going to use this function. So that means this is going to be equal to, well, I'm going to plug, this is the same thing as the limit as x approaches 4 from the negative side of 2x plus 1. I'm going to use that 2x plus 1 function. And notice that 2x plus 1 is defined at 4. This is not a sign, it's just a direction. But since this function is defined at 4, I can just plug it in. 2 times 4 plus 1, so this is 9. That's its limit. Now if I ask from when it's bigger than 4, so that means, you know, x is greater than 4. You know, I'm pointing that way, right? So that's why the other way 4. So I know I'm going to use the x squared, so if it's bigger than 4, this is going to be the same thing as the limit as x approaches 4 from the positive direction of, well, that function of x squared. And x squared is defined at 4. Doesn't matter if I'm plugging it in the positive direction or the negative direction, it's still going to be that value there. So 4 squared is equal to 16. So, you know, this one gave you 9, and then this one gave you 16, right? So from this direction, you were 9. From this direction, you're 16. So kind of our last question is, D, what is the limit as x approaches 4 of f of x? You know, does this thing have a limit? Well, calling back from our previous section, for a function that have a limit has to work from both sides to the exact same number. So the limit does not exist. It does have a left-hand limit. It does have a right-hand limit. But it doesn't have a two-directional limit. It only has one or the other. If those two numbers are the same, then yeah, then it would exist, and it would be that exact same number. I'm going to go from the negative direction, and the other one I'm going to go from the other direction. So what is the limit as x approaches 5 from the positive side of the exact same function? Okay. Well, the question is, the only new thing here is absolute values, right? It's the only thing that you probably haven't had a lot of experience with. So what I want to do is just talk about the absolute value of x minus 5 itself and what it turns into. So the question is, you know, if I just have, say g of x is equal to the absolute value of x minus 5, you know, what's another way of writing this? Well, absolute values are piecewise functions. You know, so for instance, if I ask, you know, what about like the absolute value of x? If I have h of x is equal to the absolute value of x, you know, what is h of 5? What is h of negative 5? And then we kind of talk about what happens here. Well, if we plug in 5 in here, well, the absolute value of 5 is equal to 5. And also, if you find what is the absolute value of negative 5, well, it's also equal to, well, still 5. Well, the reason why it's equal to 5 is because the absolute value sign will only change the values of negative numbers. So if it's a negative number, it's going to be opposite of that 5. That's how you take a negative 5 and turn it into a positive. You got to multiply it by negative 1. So the absolute value becomes negative 1 of that negative 5. So this is equal to positive 5. So the absolute value will become negative 1 only if the number inside is positive. If the absolute value, if the number inside is positive, then this is just going to be 1 times 5. Only time the absolute value changes to a negative 1 is when this is negative inside. So this is what it becomes. Well, sometimes the absolute value will be the opposite of what it is, right? Sometimes the absolute value will turn into a negative 1. And sometimes the absolute value will just simply disappear. And this happens only when the inside is positive or negative. So if the inside is negative, if the inside is less than 0, then you're going to have to introduce that negative number, right? But if the inside is greater than 0, greater than or equal to 0, you can just drop the absolute value sign. So I'm going to solve this side for x. So this is going to be the opposite of the expression if x is less than 5. And it's going to be the exact same expression when x is greater than or equal to 5. So I'm going to rewrite these. But the question is, what one do I use? Like, when I want to replace this absolute value, I want to replace this absolute value of x minus 5 with one of these two functions. The question is is it this function or is it this function? You know, what one do you use? Is it the top function or the bottom function? Well, it hinges on this part right here. I use the top function if I'm below 5. I use the bottom function if I'm above 5, right? So this negative one, this negative, means I'm below 5. So that means this blue function is going to turn into the, well, below 5, it's going to turn into the top function. So this is going to be the limit as x approaches 5 from the negative 2x plus 1. That thing becomes negative times x minus 5. Oh, this is still multiplication all over x minus 5. And what that means is that that x minus 5 cancels. The x minus 5 cancels, but there's still a negative there. So this is going to be the limit as x approaches 5 from the negative side of, well, 2x plus 1 multiplied by, negative 1 still. This function is defined at 5. I can plug it in. 2 times 5 plus 1 times negative 1, 11, so negative 11. This one's a little different. What does that absolute value of x minus 5 turn into? Does it turn into the top function or the bottom function? Well, this is above 5. This is above 5. It's, it's bigger than 5. So I'm going to use this bottom function. So that means that absolute value of x minus 5 just becomes x minus 5 because what's inside is positive. So I can just rewrite this as the limit as x approaches 5 from the positive side of 2x plus 1 times, that just becomes x minus 5. I should probably just put that in blue. It becomes x minus 5. It's all over x minus 5. And again, they cancel. Except they cancel now instead of the negative one, they cancel the positive one. So this is the limit as x approaches 5 from the positive side of 2x plus 1 times just 1. So this function is defined at 5. The bottom's not 0. It doesn't even have a denominator, so it can't be 0. 2 times 5 plus 1 times 1. So 11 times 1 is positive 11. So absolute values are piecewise functions. Now the last thing they taught you in this section was the sign of x over x, as long as x is going to 0. So they introduced this. They said the limit as theta approaches 0 of the sine of theta over theta is going to be equal to 1. It works for the reciprocal of this as well. So theta over the sine of theta is still going to be equal to 1. If that function approaches 1, then the reciprocal of it is still going to approach 1. All right, so example. I'm going to do it this way. So what I'm trying to do is I'm trying to build a sine of theta over theta. So whatever theta is here, I need theta is here. So in this case, I can see that theta is 5x. So if I have a 5x right here, I need the bottom to be a 5x as well. But unfortunately, I can't just pop a 5 in here. I can just drop a 5 in there because I want it there. I need to I have to multiply by 1. So in order to put a 5 in here, this is going to be the limit as x approaches 0 of, I can multiply top and bottom by 5. So 5 over 5 multiplied by the sine of 5x over x. So remember with limits is that that you can pull in and out constants, that this is the limit as x approaches 0 of 5 sine 5x all over 5x. And now I have what I need. I wanted that sine of theta over theta. I have something of that form now. So I can pull out that 5 times the limit as x approaches 0 of the sine of 5x over 5x. Now I know that this says theta. But if x is going to go to 0, then 5x is still going to go to 0. 5 times 0 is still 0. So this thing right here, those are both going to 0 simultaneously. So if this is going to 0, those are still going to both go to 0. And at the same rate is kind of what I'm looking for. They have to go to 0 at the same speed. That's why those expressions have to be identical. So that means the sine of 5x over 5x, as long as your 5x is going to go to 0, this expression here is just going to become 1. So this is equal to 5. All right, similar. Going to kind of get progressively a little messier here. So I'm going to turn this into sines and cosines. So this is the limit as t goes to 0 of 2t, and the tangent of t is going to be the sine of t over the cosine of t. And remember, our original division was that one right there, right? That's that one right here. So when I divide this, when I do this division, I'm going to have to multiply by the reciprocal of the denominator. So this is the limit as t goes to 0 of 2t times the cosine of t all over the sine of t. Now I'm close. I'm going to do a little reordering because I have a whole bunch of multiplication here. So this is the limit as t goes to 0 of, well, what I want is I'm looking for this. I'm looking for t over the sine of t. And I have that. I have my t over my sine of t. I have that expression. But I still have a 2 cosine t left over. 2 cosine t left over. Now remember with limits, you can pull in and out constants, but also the limit of the product is the product of the limit. So I can take the limit of both of these. Limit is t goes to 0 of 2 cosine of t multiplied by the limit as t goes to 0 of t over the sine of t. So this one is 1. It looks just like, I know it's the reciprocal, but I said the reciprocal is still 1. So that's still a 1. That's what that one turns into. And this function is defined at 0. If you look at the cosine function looks like this, right? And what I know, well, it looks more like that. But what I know is the cosine is defined at 0 and 2 cosine of 0. Well, the cosine of 0 is equal to 1. So this is 2 times 1 times 1, which is equal to 2. And then finally, this kind of takes that idea and these two ideas and kind of marries them. So turn everything into sines and cosines. So limit as y goes to 0 of 3, well, sine of 3y. Now this cotangent of 5y is, well, it's cosine of 5y over sine of 5y. Then on the bottom I have a y, and cotangent again is cosine over sine, but of the exact same argument. So I'm going to clean this up. I'm going to take all the denominators and put them on top by multiplying by reciprocals. So this is going to be the limit as y goes to 0. Well, I still have that 1 over y. That's that on the bottom. I'm still going to have the sine of 3y, which is this one. I'm going to have this one, since it's on top, it's still going to be cosine of 5y over sine of 5y. And when I put this one on top, it's going to flip it over. So this is going to be sine of 4y over cosine of 4, because I have to multiply by the reciprocal. Okay. So what I'm looking for is sine over, I'm looking for sine of theta over theta, or theta over the sine of theta. That or its reciprocal, just as long as theta is going to be the same. So I'm going to kind of go look at my sines. Well, here I got one of these. I have a sine of 3y. So since I have a sine of 3y, I want a 3y on the bottom as well. Well, first thing I can do is I can take this y, and that would be good. But I'm going to need a 3 on the bottom. So if I multiply the bottom by 3, I'm going to have to also multiply the top by 3. So I'm going to kind of keep track of everything right there. So this is that 3 over 3. Over here I have a sine of 5y. Sine of 5y on the bottom. So a sine 5y on the bottom. So what I need is a 5y on top. So I need a 5y on top. So if I put a 5y on top, I have to put a 5y on the bottom. And remember, I still have this cosine of 5y, so cosine 5y, that's still the numerator of this thing. And over here I have the sine, because I'm going to do it in, well, I guess, colors. Over here I have the sine of 4y. So if I have that sine of 4y, if I have a 4y, and I also need a 4y on the bottom, I need sine of theta over for the exact same theta. So if I do a 4y on the bottom, I have to do a 4y on the top. And I still have a cosine of 4y on the bottom. I really think we can take advantage of the sine of theta over theta. So that's why I only was taking sines. All right, and we still, this is the limit as y goes to 0. So now we're going to kind of go after each one of these pieces. Well, the first set of things, I can see that those y's cancel. So what I get is I get 12 over 5 here. Over here, I know that this thing, since these are, if y goes to 0, 3y is going to go to 0. So that thing is going to go to 1. Same thing here. This is also going to go to 1. Cosine of 5, well, its cosine is defined at 0. So this is the cosine of 5 times 0, which is still the cosine of 0. The cosine of 0 is equal to 1. So that's going to be 1. Times this one, which is also going to be 1. Times this one, which is going to be 1 over the cosine of 4 times 0, which is the cosine of 0. The cosine of 0 is equal to 1. So this is going to be 1 over 1, right? Which is still 1. So I have 12 fifths times 1 times 1 times 1 times 1 times 1. So this is equal to 12. All right, asymptotes. There's two types of asymptotes we talk about. We first introduce vertical ones and then horizontal ones next. And we explain how to find each one of these. And I'm going to put it all together. Let's talk about continuity, do we? Let's say continuity. We'll do asymptotes. All right, what it means to be continuous. In limits of continuous functions. Well, if a function is continuous, then the limit is simply its evaluation. So for instance, if I say f of x is equal to x squared minus x plus 2, x minus 2x plus 1, I know this function is continuous. So, it has a x minus 2x plus 1, so it's going to have, vertices that, but it's got a x-intercept here and here. Let's go look at that. Continuous, a layman version of explaining continuous. It means I can draw the picture without lifting my marker. There's no holes, gaps, or jumps. And what I know is, technically what it means is, if you look at that function, no matter what x value you choose, no matter what x value you choose for that parabola there, no matter what x value you choose, you're always going to get a y value back. That function is never undefined. Undefined things happen with denominators and radicals, right? That's when you get stuff that are undefined. That's where you get those holes. That's when you have a division of 0. So if I ask you, what is the limit as x approaches 1 of x squared minus x plus 2, this function is defined at 1. So I can just simply plug in 1. Since this function is continuous at 1, you just plug in 1 and you are good to go. So 1 minus 1, this is equal to 2. Oh, I drew it. No, it still opens up. Why did I mess that up? Oh, because it's supposed to be a minus. They're not factors. Okay, that was that graph. My bad. Better now. There's a minus 2. So this is supposed to be a minus 2. And I wanted my picture to work. Okay, so that means this spits out minus 2, which is why I have a minus 2 here. Because it's evaluated at the point 1 minus 2. If the function is not evaluated there, or it can't be evaluated there, we just talked about it. You factor it, or conjugate, and you can simplify that function to a function that's almost identical to it, except at the whole, and then you just plug it in there. All right. So, how to create a function that's continuous? So, example, determine the value of b such that f of x is continuous at x equals 3, for instance. So let's do here, let's do it this way. No, let's do x is equal to 2. Just a different number. All right. So if I want a function to be continuous, I have to do it in such a way that that you can draw without lifting your chalk. So I know that I have a piecewise function here, and I know that if I'm less than 2, it's going to be that line. It's got a y-intercept of 4, so it's going to look like this. This is going to be that line. Everywhere below 2, right? That's what that function is right there. When I'm below x is equal to 2. I know that this is another line, except I don't know its b value. So what I want is another line in there that's continuous. Well, if I put that line here, it's not continuous. Well, it's got a slope of 2, so it'll be a little higher. But if I put that line there, it's not continuous. If I put that line here, it's not continuous. What I want is that line to line up exactly at that point and do this. Now that curve is continuous. I can draw the entirety of it without lifting my marker. So how do I do that? Well, I need to find this limit, right? So here's kind of the easiest thing to do is they have to be the same y value when x is equal to 2, right? These have to be the exact same y value when x is equal to 2. So that means x plus 4 has to be equal to 2x minus b when x is equal to 2, right? So plug it in 2 plus 4, 2 times 2 minus b. You'll plug in x equals to 2, and make sure these things are equal. Well, 2 plus 4 is equal to 4 minus b, so negative b is equal to 2, so that means b is equal to negative 2. You can see if I was going to continue that graph, it would actually get negative 2. It's pretty good. So this is that b value. That's our answer. Another one might be f of x is equal to x squared minus 4 all over x minus 2. I'm going to do the same value at continuous at 2. So the way we do this is I know that that we have to kind of go through what makes it continuous. So to be continuous, the very first thing is that f of x. Oh, this needs to be a piecewise function. So to be a continuous function, f of x has to be defined at x is equal to a. 2, the limit as x approaches a of f of x has to be defined as well. It needs to have a limit. And then the last thing, kind of the most important thing, is that these two values need to be the same. That f of a if it's defined at that, that means it's another way of saying f of a exists. F of a exists. So it's defined that it means I can plug in a and then get the value. So that means f of a has to be the same thing as the limit as x approaches a of f of x. That the evaluation and the limit better be the exact same number. Okay, so let's kind of go through the steps. So here's our solution. Step 1. The function needs to be defined at a. Well, in this case, our a is 2. I'm asking about 2. So the f of 2 has to equal to, it has to exist. So what is f of 2? F of 2. When I plug in 2, what function do I use? Well, I use this function when it's not 2, and I use this function when it is 2. So when I plug in 2, I'm going to use this function. So this is going to be equal to 2 plus 2, which is equal to 4. So far, f of 2 exists. Number 2, the limit has to exist. Now, in this case, remember, this is at 2. So the limit as x approaches 2 of f of x has to exist. So remember, the limit only cares about values that are close to 2. So what function do I use? Well, this is for all values that are not 2. And remember, the limits are not at 2. They're only close to it. So this is what I need. I'm not asking for the values at 2. I'm asking for the values around 2. So I have to use that function. Not at 2. Not at 2. So this is going to be the limit as x approaches 2 of x squared minus 4 all over x minus 2. Now think factors. So limit x approaches 2 of x plus 2 times x minus 2 all over x minus 2. And you can see the x minus 2's cancel. The new function is defined at 2, x approaches 2 of x plus 2, and I can plug in 2 here. 2 plus 2 is equal to 4. How did I screw that up? This needs to be B. I gave away what it was supposed to be, but it doesn't matter. So when it's set up like this, they're going to give you a function. They're going to ask you what value of b that works. So the first, f of 2, when it's 2, it's going to be equal to that value, so it's going to be equal to b. Number 2 says that the limit has to exist. Not being close to 2 means I have to pick that function. It algebraically simplifies to become 4. Letter C says that these two things need to be equal. So it means that this thing needs to be equal to this thing. So b is equal to 4. Okay, so that's it for that. Okay, passive notes. So they give you one that's kind of start off with, and then you can kind of slide it around is what they're doing, and then we'll explain where it kind of comes from. So if I ask you this, basically it's a vertical limit. So the limit as x approaches 0 of 1 over x, well, is equal to 0 from the positive side is equal to infinity, and the limit as x approaches 0 from the negative side of 1 over x is equal to negative infinity. And they give you kind of a picture to show you why this is the truth. And I'm going to give you a little quicker hand on this. So the reason why is because 1 over x looks like this. Looks like this. So I'm approaching 0. So if I come from the positive direction, I can see that my y values, as I get close to 0, are shooting off into infinity. So they're going, as I'm getting close to 0, they're going off into infinity. That's why I get infinity here from the positive direction. And if I'm coming from, the negative direction, I can see that they're shooting off to negative infinity. So that's why I get that one, negative infinity. And they ask you to evaluate a bunch of different ones, and they just want you to kind of memorize these things. The way I kind of want you to help memorize this is, notice that you're coming from above 0. So since I'm coming from above 0, all these values are positive numbers. So what you have is 1 is a positive number. This is going to be a positive number. So a positive over a positive is going to give you a positive infinity. So that's how you have to kind of distinguish the difference between what is it going to be positive or negative infinity. And it kind of has to do with their signs. So over here, I'm coming from 0 from the negative direction. Well, anything that's coming from 0 from this side are negative numbers. So this is going to be positive, but this is going to be negative. So you're going to have a positive over a negative, hence a negative infinity. Either the bottom is going to 0 and it's not canceled. So notice. How do you know when you get infinity as opposed to another number? Well, if you plug in the other functions, every other function that we did here for limits, if you would have plugged in that number, you'd get 0 over 0, which means you're likely going to have a numeral or a, not numeral. Well, you're going to have some kind of value for this. You know, these limits are going to be, they're going to exist. But when I plug in 0 here, then it's not 0 over 0 anymore. What you have is you have 0 on the bottom, and then you have a positive or negative on top. So that's when you're going to get your infinity. 0 over 0 is going to give you a number that's not infinity, but something over 0 is going to give you a value of infinity being either positive or negative. So you have to just kind of determine the sign. So I'm going to have something over 0, so it's either going to be plus or minus infinity, depending if that's positive or negative underneath there. So notice only the denominators of it is going to 0, as opposed to the previous one where the top and bottom are going to 0. Okay, so example. Evaluate. Okay. All right, so these are the types that you're going to see. So if I want to find the limit of this as x goes to 0, what I notice is I see a 1 over x in here that I can pull out constants. I can pull out that constant. I have the limit as x approaches 0 from the negative side of 1 over x. So I can pull out that 1/5. Remember that 5's on the bottom, so it still better be on the bottom when you're done. And this value is a known value. This is this, which goes to negative infinity. How I know is that I'm going to have a positive over a negative. You know, I'm picking numbers that are below 0, so this denominator is going to be negative. So this is going to be negative infinity. So 1/5 times negative infinity is still going to be minus infinity. 1/5 times infinity is still super big. So it's negative infinity. You have ways to kind of combat this. Now, one way they show you this, and I'm gonna do it my way next. Is they make a substitution. You know, what I can do is, I'd prefer this to say go to 0. So what I can do is I can substitute x can become x minus 4. So everywhere there's an x, now there's going to become an x minus 4. So I'm going to have the limit as x minus 4, x plus 4. X plus 4 is going to go to 4 from the positive side. 2 all over x plus 4 minus 4. And what I did is I substituted x for x plus 4. I just took the thing and I just shifted it. So this is going to be the limit as x approaches, we're subtracting 4. This is going to be 0 from the positive side of 2 over x. So this is 2 times the limit as x approaches 0 from the positive of 1 over x. And this is positive infinity. I got a positive over a positive. So this is 2 times positive infinity, which is infinity. Here's a quicker way. What I know is I'm going to 4, right? And I'm going to go from the 4 from the positive side. So, you know, numbers like 5 and so on. So I'm going to 4 from the positive side. So when I'm picking numbers in here, I know that so far if I plug in 4, the bottom is going to be 0 and the top is going to be 2. I'm going to get something over 0 where the top is not 0. You know, it looks like this. So I'm going to be either infinity or negative infinity. I just need to know what the sign of the bottom is. The sign of the top is positive. It's positive 2. But what's the sign of the bottom? Well, if I'm above 4, I'm bigger than 4. So I'm just going to kind of think 5. 5 minus 4. Well, if 5 is positive, then every other number below 5 is also going to be positive. I'm above 4, so when I subtract it, I'm gonna get a positive number. So what I have is I have a positive 2 over a positive number, and a positive over a positive is going to give me positive infinity. So this is positive. The shifting is clever, but it's more work than it needs to be. Okay, for this one. This x plus 7, if I plug in negative 7, this is going to be 0, but the top is not going to be. If I plug in negative 7, 2 times negative 7 plus 1 minus 4, this is negative 13. And the top, but the bottom is going to go to 0, right? So I have something that looks like the denominator is 0 and the top is not. So that means this over 0 is either going to be plus or minus infinity, depending if I'm going to go to positive 0, if I'm going to go to negative 0, right? Depending on the sign of it. If I'm above or below 0. So who knows? We'll have to figure out what side is 0. Well, I know that the top is a negative number, so it's a negative because it's a negative 13, but the bottom. So here's our negative 7. Negative 7, here's some other numbers. So negative 6, negative 8. I am above it, so I'm over here, right? I'm above it. So if I plug in negative 6, negative 6 plus 7 is positive. You know, any number that's above the 7 is going to be positive, so this is going to be positive. So a negative over a positive, this is going to be negative infinity. The other limits that these are called vertical limits. You know, they have vertical asymptotes. That's what's going on here. As if this thing has limits that go to plus or minus infinity, is because 1 over x has a vertical asymptote. So this has a vertical asymptote at 0. This has a vertical asymptote at 4 because I'm shooting off at infinity. And this function right here is a vertical asymptote at negative 7. Horizontal asymptotes are where the limit itself is going to 0. So right now the y values are going to infinity or negative infinity. What happens if the x values go to infinity and the y values go to a number? Horizontal asymptotes. And it doesn't matter the direction. As x approaches plus or minus infinity, 1 over x is going to go to 0. And what happens here is, if you're going to look at the graph of this, our 1 over x, you know, our function 1 over x, looks like this. And if I go to positive infinity, or if I go to negative infinity for my x value, remember my x value, my x-axis, my x value, it doesn't matter. In both cases, I'm going to this asymptote, right? So in both cases, that asymptote is y is equal to 0. So that's why I get 0 back. All right, so examples on how we do that. So how we do these, the asymptotes as x goes to infinity, is we multiply top and bottom by 1, but it's going to be taking advantage of our we take advantage of our the expression that has the highest power. So we're looking for the leading power. So the highest power I see, the highest, you know, I should have made I'll make this x cubed. Squared x plus 2 x cubed. So what I see over here is, in both cases, these have an x squared in it. This is the variable to the highest power that I see. So what I'm going to do is I'm going to multiply top and bottom by 1, but I'm going to do it in such a way that I'm going to cancel that highest power. So I'm going to multiply top and bottom by 1 over x squared, taking advantage of the highest power. So when you distribute this to all the terms, so you're going to get the limit as x approaches infinity of 2x squared over x squared plus x over x squared minus 5 over x squared And then the bottom is going to be x squared over x squared plus 1 over x squared. And a bunch of stuff cancels. So this is going to be the limit as x approaches from infinity of 2 plus 1 over x minus 5 over x squared all over 1 plus 1 over x squared. And what I notice, I know that 1 over x, if I'm plugging in infinity, is going to go to 0. Or even 1 over x squared. You know, if the bottom is going to go to infinity, this expression is going to go to 0. The same thing here. This is, 5 over x squared. It's the same thing as 5 over 1 times 1 over x times 1 over x, right? And that goes to 0, and that goes to 0. So the product and limits limit the product. So you can still just, this is going to go to 0 as well. So what you get back here is 2 plus 0 minus 0 all over 1 plus 0. So this spits out 2, which is neat. That means the horizontal asymptote of this original expression, this one right here, horizontal asymptote of that thing is 2. If I want to find the horizontal asymptote of this, I'm going to do the exact same thing. But I'm going to look for its highest power. Highest power is seeing all this as an x cubed. So I have to do 1 over x cubed. 1 over x cubed. And then when I multiply this is going to be the limit as x approaches infinity of 3x squared over x cubed plus 2x over x cubed plus 2 over x cubed all over x cubed over x cubed minus 4x squared over x cubed plus 7 over x cubed. I know a little tedious, but it is what it is. At least it's all correct. So this is going to be the limit as x approaches infinity of 3 plus 2 over x plus 2 over x cubed. The bottom is going to be, this is 3 over x. This is x squared. Okay. And then the bottom is going to be 1 minus 4 over x plus 7 over x cubed. And what I know is that anything that has an x on the bottom and a constant on top is going to go to 0. 1 over x. If it's going to infinity, it's going to go to 0. If it's going to 0, it's going to go to infinity. It's kind of neat how these things kind of switch places, right? And if x goes to infinity, then the y value goes to 0 for this function. But if I go to 0, I'm going to go to infinity. So the vertical versus horizontal asymptotes. So this is going to be equal to 0 plus 0 plus 0 all over 1 minus 0 plus 0. So I have 0 over 1, and 0 is a lot in the numerator. You get 0, so that's the answer to that one. So 0. All right. I want to graph a function given some information, and then I'm going to go backwards and ask you to verify things. I want to find this stuff. So this is like 2.6. So example. this just comes down to understanding what these things mean, and then we're going to kind of patch the rest of it together with some curves. So what does it mean? Well, what the first two mean, these are just points. Points on the curve. The first one means that it goes through -1, 5, and the next one means it goes through 3, 7. So far in my graph, I have -1, 1, 2, -5. 1, 2, 3, 4, 5. So it goes through -1, -5, and it goes through 3, 7. All right. Next, it says, as I approach 1 from the left, it's -infinity. As I approach 1 from the right, that's positive infinity. So if you're shooting off into infinities and negative infinities, you're talking about a vertical asymptote. This means vertical asymptote. So it's a vertical asymptote at x is equal to 1. So at 1 right here, got a vertical asymptote. And what I know is I know that if I'm approaching 1 from the negative side, I'm shooting the negative infinity. So if I'm approaching, I'm shooting the negative infinity from this direction. And if I approach 1 from this side, it's going to positive infinity. So it's going to go to positive infinity. Last thing I know is that as x goes to infinity or negative infinity or infinity, well, if I go to negative infinity, this is going to be -2. Now this is a piecewise function. They don't usually have different horizontal asymptotes. So these are horizontal asymptotes. Student blue. Horizontal asymptote. And that means I have two of them. I have y is equal to -2 and y is equal to 4. So I have a horizontal asymptote at -2. I also have a horizontal asymptote at 4. Now the only way for this to happen is if it's a piecewise function. And I could create something to make it work, but it's fine. Okay, now let's see what that means now. Now it says as I approach negative infinity, I'm going to -2. So as I'm going to negative infinity, my x value is going to go to negative infinity. I'm shooting off to negative infinity. That means the y value is going to -2. So I'm already below this. So it means this is going to have to go to -2 and shoot off to negative infinity. There goes the 1. Now over here it says as I approach positive infinity, x goes to positive infinity. That means the y value is going to go to this 4. So it's going to. So that's a graph that has those properties. It goes to those 2 points. It has those infinite limits as I go to 1 from the negative and 1 from the negative, 1 from the positive. So negative infinity, positive infinity. And also as I approach infinity for the x values, I go to -2 for this one, and I go to negative infinity, and positive 4 when I'm going this way. All right, I'm going to give us a function, and I want to find all the information of this function, removable discontinuities, asymptotes, and this is kind of like putting everything together. So this is why 2.6 is here. Okay, so okay, I'm gonna do it this way. All right, so let's start this up. I got all the material. And I want to find x and y intercept. B, I want to find vertical asymptotes. Using limits. C, I want to find horizontal asymptotes. Using limits. And then last, let's graph it. From the above information, of course. All right, so solution. A, x-intercept happens when y is equal to 0. So this is when 0 is equal to this function. I'm gonna factor this because I know it does. So this is x minus 2 times x plus 1, and the bottom is going to be equal to x plus 1 times x minus 1. So my x minus 2, x plus 1, all over x plus 1 times x minus 1. Actually, I could have got rid of that. Those cancel. So this is when 0 is equal to x minus 2 all over x minus 1. Multiplying both sides by the denominator. So 0 is equal to x minus 2. So x is equal to 2. So that means I have the point 2 comma 0. You know, x is equal to 2, y is equal to 0. In a y-intercept, that happens when x is equal to 0. Much easier, by the way. You're just plugging in x equal to 0 into this expression. You can use this one or this one. So y is going to be equal to 0 squared minus the 0 minus 2 all over 0 squared minus 1. And plus, if you plug 0 into all these, negative 2 over negative 1. So you're going to see that negative 2 over negative 1 is going to give you 2. So that means I have another point here. X is 0, y is 2. So I have 2 solution points. That's what the intercepts are. So I have points here and here. B, I want to find vertical asymptotes. What I notice is that talk about what happens when it cancels. Oh, actually, I should say D. I need to find any removable discontinuities. And then finally, E, we're going to graph. So B, finding vertical asymptotes. Well, vertical asymptotes happen when the bottom is equal to 0 and only the bottom is equal to 0. So what I can see is that if I'm using negative 1 I would have 0 over 0, so that means it's going to be a hole. But if the bottom is equal to 0, that's going to be asymptote. So this is only going to happen at 1. So this would happen when x is equal to 1. So when I want to do that for a vertical asymptote, I know that I have to use limits. So that means I'm going to take the limit as x approaches 1 from the negative side of this function of x minus 2 all over x minus 1. And I'm also going to take the limit as x approaches 1 from the positive direction of that exact same function. I'm using the simplified version because I'm not plugging in negative 1. I'm only plugging in positive 1. All right, so what I'm going to have is the top is 1 minus 1, so the top is going to be negative. Now this 1 comes from the negative side, so if I'm at 1 right here, coming from that negative side, so if I'm coming from that side, that means I'm below 1. So values below 1, so like 0.5 or 0 minus 1 is going to be, that's going to be negative on the bottom as well. So a negative over a negative is going to be positive infinity. So I got a negative over a negative divided by a negative, which means I'm going to get positive infinity. Now over here, I'm approaching 1 from this positive direction, so I'm coming from that direction. So the number is bigger than 1. So, 1 minus 2 is still going to be negative on top. But value is bigger than 1. Well, number is bigger than 1. Numbers bigger than 1 minus 1 are going to be positive. 2 minus 1 is positive. It's going to be positive on the bottom. So positive over a negative is going to be negative infinity. So that's what happens when the bottom is 0, the top is not, right? We get infinities. We just have to keep track of their sign, plus or minus, to determine if it's positive or negative infinity. So there's our vertical asymptote, and I'm going to be able to draw it pretty soon. C, horizontal asymptotes. Well, that happens when x is going to go to infinity. So I'm going to take the limit as x goes to infinity of my x squared minus x minus 2 all over x squared plus 1. Or I could use the simplified function as well. So you're welcome to use the simplified function as well, because I'm not going to -1. I'm not going to where that expression is equal to 0 there. So multiply the top over 1 over x squared, 1 over x squared. It's how I handle the infinite limits. So this is the limit as x goes to infinity of x squared over x squared minus x over x squared minus 2 over x squared all over x squared over x squared plus 1 over x squared. And we're going to get the limit as x goes to infinity of 1 minus 1 over x minus 2 over x squared all over 1 plus 1 over x squared. And when you go to infinity, those terms will be 0. So 1 minus 0 all over 1 plus 0. So this is equal to 1. Remember that means y is equal to 1 is our horizontal asymptote. It's a horizontal asymptote. You know, it's its limit that's the horizontal asymptote. What's funny is the vertical asymptote is where the x value goes to, right? Because these are going to go to infinity. So these are going, the y values are going to infinity. That means this x equals 1 is a vertical asymptote. But in this case, the x values are going to infinity. That means that the y values are going to 1. That means those are horizontal asymptotes. So kind of knowing the difference. Or kind of putting it all together. D, any removable discontinuities. Well, that happens when you get 0 over 0. And it's only going to be 0 over 0 if I plug in -1, because that x plus 1 cancels when you plug in -1. So this is going to be the limit as x goes to -1 of x minus, x minus 2 all over x plus 1 all over x plus 1 times x minus 1. Those will cancel. So the limit as x approaches -1 of x minus 2 all over x minus 1. So I get -1 minus 2, -1 minus 1. So I'm going to get -3 over -2. So I get 3/2. So what that means is there's a removable discontinuity, or there's a hole is another way to write that. There's a hole at -1 3/2. All right, finish this off with the graph and fit it in here. That'll be it for class, for this lecture. So I go through 0, 2, and 2, 0. So there we have those. I have those as points. I have a vertical asymptote at x is equal to 1. So vertical asymptote at x is equal to 1. And I have a horizontal asymptote at 1 as well. So this x equals 1, because it's the x value where these things are going to go to infinity. And I have horizontal asymptotes at 1, because that's when x goes to infinity, y is equal to 1. So I have a horizontal asymptote at 1. And we got to follow the trend too. So what I know is, kind of finishing this, if I go to 1 from the negative side, it's going to shoot to positive infinity. So this is going to go to up. And as this goes for plus or minus infinity, by the way, because it's not a piecewise function. So if I go to negative infinity, this is going to go to 1. Now here, if I go to 1 from the positive side, I'm shooting off to negative infinity, or the negative infinity from the positive side, and then the y value is going to have 1 as well. The only thing I'm missing here is that this function right here has a hole, at this x, at wherever makes x plus 1 equal to 0, which is at -1. So at -1, this thing has a hole, and that value is going to be 3/2. So at -1, that point right there is the whole -1 3/2. So that's the graph of it. That's everything. This is the final answer for our graph. Okay, so hopefully that kind of puts everything in perspective as far as why we're doing it all. That's 2 hours of explanation. I'm gonna. If you guys got more questions, come to my office hours. Happy to help.